Thanks very much. So you can see the data the paper came out, which was a while ago, and we should have another one next week, and then some number n after that. But I've been working on this stuff with my collaborators for quite a while, and it's exhausting, frankly. So it's disk amplitudes, you know, 1 week you're computing these horrible string amplitudes, and the next week you're digging through literature from the 1980s to get certain things to work, but they were doing disk amplitudes, but they didn't really know about E-frames, the generalized things. In principle, everything's there, but it's exhausting. So it's hard to get up in the morning sometimes to face along with these calculations. And so to inspire myself, I tell myself a story. So I want to tell you guys a story to start with. So once upon a time, we wanted to put M theory on the output ports. And we wanted to maybe add some fluxes. There's this four-form flux in M theory. And we probably want to preserve supersymmetry because we're not that bold yet. So you do this, and then you say, okay, let me try to just solve the equations. And so I write down my low-energy effective theory. And one of the equations I'm trying to solve turns out to look something like this. So here, F is just some function on the Flabiau related to some warp factor in your solution. G4 is a four-form, closed four-form on the Flabiau that's got integral periods, roughly. I might have some delta function sources around. So this is one of the equations I'm solving. If I integrate that over my compact space, I get this here, where n is a positive integer, and this is the integral of a positive number, and this is supposed to be 0. So I say, oh, what a terrible result. I guess I can't have any flux. G4 must be 0. I can't have any M2 branes. N must be 0 if I want to preserve supersymmetry. How boring. But that would be wrong. Which was recognized by various people. So what I neglected to add here was that there are higher derivative corrections. So this is some 8th derivative correction. The action that enters this equation of motion. So these guys are 2 derivatives. This guy's 8 derivatives. There's some factor of L pointing to the 6th up front. X8 is some 8 form built out of curvature tests. There's 4 curvature tests. And if you're just interested in locally solving, say solving for this function f, locally you're perfectly legitimate to ignore this. It's going to typically be much smaller than things like this, which have just 2 derivatives and go like 1 over the radius of the space squared roughly locally. This guy goes like 1 over the radius of the 8. But when you integrate it over, what happens is that the 1 over radius squared parts here get washed out, and you just get the sort of topological contribution, which is some integer. You have this integer to the 4, and now the integral of this guy over the full compact space gives you something proportional to the Euler character of the Flabiau portion. So again, this was a pretty well-known result. But now this is a much better situation. So for fourfolds, most fourfolds chi tends to be positive, and so you can have solutions here. In fact, on a typical Flabiau fourfold, what happens is that fluxes and branes have gone from being forbidden, they just weren't allowed in the equation of motion, so now they're actually required to get a solution at all. So the higher derivative term really mattered here. It didn't matter in locally solving the equation, but it mattered in determining the consistency of that. So let me translate my little story into 2B language. You just do if your fourfold is elliptically fibered, you can decide that fiber is 0. You get seg 2B on the base of the fibration. Dilaton, 7 branes, and 7 planes, and so on. And you get an expression like this. But now, so type 2B, the Flabiau fourfold is sort of an auxiliary thing. It's not theory thing. So it's not totally clear where that chi over 24 comes from when you first look at this. This wasn't totally clear to me. You might guess that it's the same thing. There's some higher derivative corrections to the type 2B action. Well, that doesn't quite work because type 2B, like M theory, doesn't receive corrections until 8 derivatives. But now your compact space is just 6-dimensional, and you can kind of convince yourself that those contributions are not going to give the type you want. The dimension is basically just going to go. But there's other ingredients that come when you do this duality. So places where the vibrations are generated, those become D7 brains and O7 planes and so on, that wrap 4 cycles of this internal, of this base-to-base beam. And the action on the brain can receive a 4 derivative correction, and that 4 derivative correction integrates over that 4 cycle into the number. And in fact, that's exactly what happens. So the 7 brain action, for instance, has a 4 derivative correction that looks something like this. The equation of motion I was trying to solve in this context is basically a tadpole C4. It's the equation of motion for C4. So I get this extra contribution integrated over a 4 cycle, and that precisely rebuilds the Euler character of the Labial fourfold on which you put F3. It's kind of a cute story. The moral of my story is that we really need to understand these higher derivative couplings of D-brain actions if we even want to really make solid claims about the consistency of vacuum. So if we want to study the space of string-free vacua, we should understand these things. And so I tell myself this story in the morning, and I resign myself to a hard day of this thing. Okay. So now let's get to the nitty-gritty of things. So those trace R-squared corrections that I wrote on the previous slide are not the only ones. Not the only ones at 4th derivative order. And so one of the easy ways to see that is just looking at consistency with T-duality. So we sort of know how D-brains act in the T-duality, and T-duality mixes the metric, the closed string metric, with the closed string B field. So if we've got terms like trace R-squared, which involve derivatives of the space-time metric, there should also be, by T-duality, terms that involve derivatives of the B field. And then so in this paper, we have Thatcher Becker and Swanky Rowe, we did that. We linearized those trace R-squared couplings. We imposed consistency with linear T-duality, and we found that, so this is basically, so if X4 was trace R-squared, this would be the term I had before. So now, in addition to that, I'm going to get terms in that 4 form which look like 4 derivatives acting on B fields.
Now, H is supposed to vanish, right? So, on the D-brain world column? Right. So, you're a little vague on the derivatives of
that's right. That's right.
But presumably, there are
that's right.
things which involve H that you can throw away.
Things which involve H pulled back to the lower profile.
Yeah.
Yes, that's right. So you get things which involve H, but with legs normal to the brain and things like that. Right. So you get some big complicated things basically. So yeah, many of these derivatives involve normal directions. Okay. Especially in these cases. Yeah. So you get that addition to the the C4 term, say. But then you also get other terms involving remote fields with legs normal to the brain. So that was a surprise. So this T7 brain doesn't just couple with C4. In the presence of non-vanishing B fields, well, actually even without non-vanishing B fields, you will get coupling to C8. Well, that's not what's coupling, but C8 with legs, 2 legs normal to the brain, or to C6 with 1 leg normal to the brain. And these just have to be there by T-duality. And then we went out and this was surprising. And maybe there were some places in the T-duality analysis that worried us very slightly. So we went and computed some discount pursuits and verified that these terms really are there. Okay. That's it. But now, doing this linearized T-duality has created some extra terms. Those terms too are not going to be the whole story. So the terms we generated had many failings. So by themselves, they weren't gauge invariant. We didn't impose any kind of nonlinear consistency checks and so on. So we really wanted to just write down some full 4 derivative action. So one way is to really work, just grit our teeth and work with full nonlinear T-duality, impose gauge invariance, homomorphism invariance, and all this. This gets very messy because you're complicating things in 2 dimensions. So we all know that things get harder when you add derivatives because there's just more terms you can write down. Things also get harder when you're working with D-brains because you've got some submanifold essentially. And so consistency with different morphisms means we're writing things in terms of second fundamental forms and things like that. And so when you're doing both at the same time, things just get awkward. There's hundreds of terms you can write down. The nice and consistent, and then you have to really turn a very large crank to work things out. So the other thing you can do is do these computations with disk amplitudes. So there are definitely drawbacks to that as well. You only get on-shell information for your external states that you're forced to do on shells. And there's a layer of processing which I'll get to subsequently. So the best way is really to do both these techniques together, which is what we're doing in honor of a paper that should come out next week, which is basically written in just being proofread. I'm going to focus on the disk amplitude. So what happened was when we computed these couplings that I showed you before with T-duality, and then we checked them with disk amplitudes, we got very confused by a lot of details. Because we maybe never sat down and really tried to do honest disk amplitudes before. And there are a number of things that were actually confusing the heck out of us. There's this BRC exact states maybe don't generically decouple from disk amplitudes, so you have to worry about that. Picture changing, you will prove that things are independent. The picture doesn't really go through on disks the way it does on spheres, closed Riemann surfaces, that way. So there were a whole bunch of things that worried us, and basically we spent an inordinate amount of time trying to get everything straight. And I think a lot of the information I'm going to tell you is definitely not new, but it was sort of new to us, and then we tried to work it all out in our own formulas and stuff. Now we're really ready to just compute what we're doing. Okay, so let me go through the steps we wanted to do. So we need to construct the physical state operators using some BRC quantification or something like that. We want to construct a boundary state. We're going to work with the boundary state formalism. We have to make sure all of that was straight. Then we want to show that the amplitudes we're actually computing really didn't depend on sort of physically relevant choices like which gauge represents the took, or how we distributed picture charge and so on. And if it wasn't independent of those choices, then we have to say what the right choice is. Really, at the end of the day, we're interested in some space-time actions, which hopefully should be unambiguous. And then we're going to compute the amplitudes, and then we're going to try to compare to field theories to really try to nail down those questions of the actions. So this is a lot of work, and it's definitely a lot to cover in 7 minutes or something. So it'll be very brief, but I'm happy to talk at length about any of these things later. All right, let me quickly go through some of the things we relearned, let's say. So to construct physical state operators, it turns out we need to use these semi-relative BRC homologies. This goes back to results by Nelson, Jacques, other people. So what we're supposed to do is we're supposed to start with states that are annihilated by B0 minus B0 tilde. These are some zero modes of dose fields and mutual gases and quantization. And then we take cohomology with respect to the total BRC charge. So for the purposes of today, we're interested in degree 2 cohomology in particular. So it's dose number 2, total dose number 2. So it turns out L0 commutes with BRC and commutes with B0. So we can restrict the state to that well-defined conformal weight. Similarly, the momentum operator commutes with the state to well-defined momentum and well-defined picture charge. So if we take conformal weight non-zero, it's pretty easy to show that your state is going to be BRC trivial. So we're going to set the conformal weight to 0. That's when we're building the state including those. So there's old results. Well, in the bosonic string it was Frenkel, Garland, and Zuckerman, and it was generalized to the superstring by Nian and Zuckerman, and they showed, well, essentially that if you've got non-zero momentum, so PU is not zero, then it's ghost number, the BRC homology is trivial except ghost number 1, 1. I'm lying here slightly. There's an extra set of isomorphisms you need to show, but basically that's correct. So that's a useful result we did, and sort of went through all the steps to go there. They only did it in a particular picture. If you look carefully at what they were doing, they start with a particular picture vacuum and then get a finite numbers of oscillators and then change the picture. But there's also a result by Berkowitz and Spivak where they constructed picture-changing operators. The usual picture-changing operators don't work so well in the semi-relative homology because the picture-lowering operator doesn't commute with these amounts. So that's a problem. But it turns out you can, if the momentum is non-zero, there's a different picture-lowering operator you can construct, which will do the trick. Berkowitz and Spivak showed that. So now for all pictures, we're okay. We know how to compute. We can really restrict down to this sort of finite space of operators. Everything's finite, and we just do a homology there. So, all right, we've got our physical operators. That's good. Now to say some words about the boundary state. So schematically, what the boundary state does is it's a state you were going to insert on a sphere and then sort of propagate out to finite size, and it implements the boundary conditions on the field. So it's basically representing the D-brane coming in. So it implements these boundary conditions. So these again techniques were well established long ago for these guys. We tried to do something slightly different than what we've seen in literature, which is really derive all the properties needed for the boundary state without ever actually explicitly writing down boundary state. So just from the boundary conditions that you need to satisfy, you can work out GSO projection, how business correlators, and all this. So we worked out on that. Boring, but it was very real stuff this time. All right. So now this was one that worried us a lot. So the decoupling of the RSC. So it turns out that part of this propagator is sort of the boundary state, some gross insertion which doesn't commute with the VRC charge. So the usual proof that the VRC exact states decouple from amplitudes doesn't go through. So in fact, what you get instead is if you plug in, let's say we do a 2-point function on the disk, I've got some VRC closed operator here and some VRC exact operator here. So it turns out that the amplitude on big S is still somewhat schematic. Don't worry too much about it, but it's basically a boundary term evaluated at r equals infinity and r equals 1. And if you put in so a priori, there's no reason, if I don't tell you anything more about E lambda, there's no reason those boundary terms should vanish. No reason they have to vanish, but I know. However, maybe we believe that V and lambda both have generic momentum, and we believe that our amplitude should be analytic in lambda. So in that case, then we can evaluate. So near r equals infinity, you're going to get something like r to minus 2 p1 dot p2 plus some constant that's independent of p. So great. So now we can continue to different regions of momenta, and basically this is going to be either infinity or 0. Well, if it was infinity, our integral is sort of that this was boundary term up is not convergent within what we find anyway. So essentially, we say that this, we can continue to a region where this was 0, and by analysis the HB 0. So that's our argument that these things decouple. And this argument will actually break down for in certain non-generic situations. For instance, if the D-brane is very low dimension or very low codimension, one of these guys may be forced to be 0 just kinematically, and you don't have this continuation available. There, you probably really have to modify your vertex operators. Boundary terms, it's going to get messy. We're going to basically, we're mostly interested in branes in sort of middle dimensions, shall we say. So we can safely ignore this. Everything in VRC states will decouple, and this also demonstrates by a couple of lines that things are independent of how you distribute the So we go through that argument very carefully. All right. One more thing is that so we go into computer amplitudes. Now we want to compare field theory. The difficulty there is that, let's say I do a disk amplitude with 2 insertions of the dilettante field. So that's one string theory amplitude. But if I want to compare with field theory, it's getting contributions from 3 different diagrams. So if you fatten out all these lines, then these 3 diagrams are all topologically paratangent basically. So you get these 3 amplitudes. This is the guy we really want to find, perhaps, is this 2-point function that lives on the brain. So we have to figure out ways of subtracting these guys. This guy's easy because we know that at the order we're working, the bulk vertices is going to get in this direction, so it's easy to subtract this guy off. This guy, we have to be maybe a little bit more careful. It's all doable. So let me just finish by telling you what we're doing now. Now we're just computing. So we're going to be able to write down. This is what we get for, say, a linearized order, the third order in fields. We're going to be able to write down the brain action of order those. And we're hoping that we'll be able to rewrite things in all those different terms. Hormone fields, which along the brain, maybe some things normal to the brain, in some way that looks nicer and is maybe well motivated from some more interesting perspective. So, the trace R squared could be rewritten in terms of this, which has some justification in terms of pairing, implicit K theory. So now we've turned on some maybe H flux in the bulk. We should have some twisted K theory. Hopefully, the result we get can be rewritten in something like that, but we've not figured out how to do that yet because we're still trying to nail down all the coefficients. All right, I'll stop. Time for a quick question? Well, unless the next speaker down.